Thank you. This is Wenxing. I'm very happy to have this opportunity to present my work, two-way transit signal priority algorithm for optimizing transit reliability and speed using a deep reinforcement learning approach. So the motivation for us to develop this transit signal priority TSP algorithm are mainly because the first reason is that transit reliability and speed are both key performance indicators for transit agencies and users. Second, transit services are vulnerable to variability and delays, especially in busy networks like we know in Toronto. Third, currently there are no strategies that can improve these two performance indicators simultaneously. So this is an obvious research gap. Fourth, although there are TSP applications that address transit reliability, the majority of TSPs in the field focus on reducing delays only. And fifth, simple first come first serve logic are often used to handle multiple TSP requests from different approaches, regardless of real-time performance. And the last reason is that many TSP algorithms rely heavily on models of the dynamics of the transportation environment, which usually contain assumptions. So to overcome these limitations, we developed a dual objective TSP that adaptively optimizes reliability and speed. This system includes a coordination algorithm that handles requests from opposite directions, which provides solutions considering real-time bus performance. As transit passengers, we may ask, why not improving speed only? And why do we want to also emphasize reliability or say headway regularity? We know that improving headway regularity and reducing transit delays are both important. Uneven headways like long headways result in crowdedness at bus stops, and short headways lead to bus bunching. Passengers travel on bus lines with irregular headways experience excessive wait time, which is out of vehicle travel time. And in-vehicle travel time is increased when there are transit delays, and a great portion of which can be attributed to traffic light. So our question becomes, does there exist a single strategy that can adaptively improve both headway regularity and travel time? Our current answer is no, because current transit signal priorities are effective in reducing signal delays, but does not guarantee an improvement in reliability. And that's why we want to develop a transit signal priority algorithm that is able to improve both at the same time. So to solve this dual objective TSP optimization problem, we applied model-free deep reinforcement learning. Compared with tabular Q-learning, deep Q-learning is efficient for large state space. And we rely on the infrastructure that we have now in Toronto, which are the loop detectors to collect transit and traffic data. So these data are used for online training of our deep reinforcement learning agent. A check-in loop detector is located a few hundred meters upstream of an intersection, whereas the checkout loop detector is immediately downstream of the stop line. As shown in this figure, the zone between the check-in and checkout loop detector is the priority operating zone. We call it POZ. Our deep reinforcement learning agents are developed for one way only. So we have two independent agents, one for each direction. So this slide shows 4 essential elements of reinforcement learning and how they interact with each other. Reinforcement learning is a subfield of machine learning that teaches an agent of how to choose an action from its action space within a particular environment in order to maximize rewards over time, and in our case is to maximize the headway improvement and reduce travel time. And reinforcement learning has 4 essential elements. The first one is environment, which is the world, real or virtual, in which the agent performs actions. In our case, is the transportation network simulated in AIMSA. And the second element is agent, which is the program we train with the aim of doing a job we specify. In our case, the agent is the TSP control system, which interpret the environment state, including information related to bus headways, number of cars, and signal timing. The agent also receives reward feedback from the environment after an action is taken. So the third element is action, which is a move made by the agent, which causes a status change in the environment. We adjusted the duration of the green phase for buses using truncations up to 20, 15, 10, and 5 seconds, and extensions up to 5, 10, 15, and 20 seconds. The last element is reward, which provides the evaluation of an action. So in our case, the reward consists the evaluations on the headway improvement and the travel time in the priority operating zone. So in general, using reinforcement learning, the traffic signal control system collects information on the states of the environment, takes an action, and learns the quality of different actions via the feedback signals provided by the environment. The coordination algorithm connects two different reinforcement learning agents, X and Y, and decides which actions to take when there are multiple requests from opposite directions. If both directions have buses, the coordination algorithm takes the Q values from two reinforcement learning agents and outputs an action that maximizes the weighted sum of Qs. So the Q values represent the quality of each and different actions. We can design the weights in multiple ways. For example, we can give higher weights to the direction with higher passenger loads or larger headway deviation. The proposed TSP algorithm is trained and tested in a carefully calibrated micro-simulation model using AIMS-on-Next, which simulated a subnetwork in the city of Toronto. The bus line 36 Finch West is operated on the east-west corridor, which experiences very high service variability. We'll collect field data on traffic demand during AM peak and automated vehicle location data from TDC to calibrate traffic and transit performance. And all signals along the corridor are simulated based on signal timing cards provided by the City of Toronto. We trained and tested our two-way TSP at this intersection to see if the performance of this bus line is improved. The performance of our two-way TSP is compared with 3 baseline scenarios. The first scenario is no TSP, which uses a fixed signal timing plan currently serving the selected intersection with TSP disabled. And the second base scenario is TSP, what we call a Toronto TSP, which uses the background timing plan and no TSP scenario with TSP algorithm currently used in the field enabled. And the third one is the first come, first served TSP, which also uses the background timing plan and no TSP, but with the first come, first served TSP. So this algorithm also contains 2 different reinforcement learning agents. Instead of using a coordination algorithm, it uses the first come, first served logic that provides TSP only to the bus in the direction that comes first. All these base scenarios are compared with the proposed, what we call a D2 TSP. So that's dual objective two-way TSP, which consists 2 different reinforcement learning agents and the coordination algorithm as explained earlier. We first take a look at the reliability performance, and we use coefficient of variation of headway as the measure of reliability, which represent headway adherence. So the two-way TSP is shown on the right end of this figure. Red bars are eastbound, blues are westbound. The developed TSP, our two-way TSP has the lowest coefficients in both directions, which means the lowest headway variations and the best reliability performance. So this slide, we want to assess and demonstrate whether our two-way TSP is able to reduce bunching and large headway gaps. So this slide shows the percentage of extreme headways, naming headways below 25% of scheduled headway, below 50% of scheduled headway, more than 150 and 175% of scheduled headway. So the red columns are the developed two-way TSP, and it's apparent that our D2 TSP has the lowest percentage of very high, of very short and very long headways in all cases. So this slide compares travel time of all scenarios. No TSP has the longest travel time in both directions. Toronto TSP and first come, first served TSP have the shortest travel time in eastbound and westbound respectively. The D2 TSP provides noticeable savings compared with no TSP, but not as much as Toronto TSP because Toronto TSP grants priority service to all detected buses, including early ones. While D2 TSP also has to consider headway performance, it does not always expedite buses. Therefore, it is within our expectation that D2 TSP would not have travel times as short as Toronto TSP. We want to ask how much travel time is traded for headway improvement. So we compare the D2 TSP with Toronto TSP, which has the shortest travel time. On average, 9-second increase in travel time is traded for 23-second improvement in the standard deviation of headway. And we performed some calculation and got that this 23 seconds reduction is equivalent to a 10-second saving on expected waiting time for passengers at this bus stop. As a rule of thumb, the waiting time is valued twice as much as in-vehicle travel time for non-business trips, which means this 10-second can be further translated to 20 seconds perceived time cost as in-vehicle travel time. To conclude, our two-way TSP generates the best headway performance in both directions. It is effective in reducing headway variability and percentage of extreme headways. It also brings noticeable reduction in travel time compared with no TSP. Some future work. Even though the standard deviation of headway and coefficient of variation of headway is improved substantially using D2 TSP, trying to restore headway at one single intersection may not be always achievable. Future research can be conducted on developing a dual objective TSP coordinated at multiple intersections to gradually enhance the transit reliability and speed performance. And loop detectors used in this study are not able to provide continuous data. So this limitation can be overcome by applying connected vehicle technologies, which will support more informative decision-making. Moreover, we can consider integrate TSP design with other route strategies like dynamic transit lanes and bus platooning. So in the end, I would like to thank Huawei Canada Research Center for their funding support. And this is the end of my presentation. Thank you.
Okay, thank you so much, Ariel. Again, very interesting work. You have a couple of questions waiting for you in the chat box. But can I maybe just ask you to elaborate a little bit more about your thought about coordinated TSP? I know you're working on this now. Maybe if you can just shed some light on, how you expect really to improve reliability by coordinating the TSP actions along consecutive intersections.
So the reason why we're considering coordinated TSP is that we know that at single intersection, we may achieve some savings in travel time and some reduction in headway variability. So at downstream intersection, we do not want this gain to be canceled. So we want to enhance our gain from the downstream intersection. And we know that there is coordination between two intersections based on the bus performance, also based on the traffic demand. And so there are situations where we might be able to sacrifice a little bit at the upstream intersection, but achieve a higher gain at the downstream intersection. And that's why we want to consider coordination between intersections.
Yeah, sounds very intriguing. I can't wait to see the results. That's pretty exciting. Well, thank you so much to all the speakers.